So when we have this report in Revit, we have a lot of information here, very useful. We have the envelope and we have the heating loads through the roof, through the glass, conduction and solar. This is cooling. So solar conduction, if we are in this room, in the meeting room with a lot of glass, solar is always the most relevant heating cooling load that we can have. And here we have infiltration. Okay, so in infiltration, in summer, in cooling, it's very low, it's 27. In heating, it should be higher, okay? So infiltration means that the outdoor air is entering the building without any control. So the outdoor air in summer or in these conditions, this dry bulb was 77, which is not far from the comfort temperature. Okay, so that's why the infiltration load is not that relevant in summer, but in winter, the infiltration load, it's quite high. It's the second highest. Okay, so you see that we have 9,000 for the glass conduction, but in the second highest is the infiltration load. So we don't know what Revit does to calculate infiltration loads, but we don't know. Probably in the software they explain what they do and what formulas they use, but it's very difficult to understand what Revit does. So we just have to trust Revit on this number. Is there a way to calculate infiltration? It's quite difficult because infiltration depends on the way the build has been built. Okay, so if it's a high quality company, we will have fewer infiltration loads. But if the company or the building doesn't have a good quality and we have cracks and the sealant is not well, so we might have a lot of infiltration loads. So there is no way to test that in a simulation. We have to test or we have to carry out a real test, which is the blower door test. I hope that we can have a blower door test at least for you to realize how it works and what the results are. So we will select one of the buildings, not this one, but one of the old buildings that we have on campus, and the results will be terrible, okay? But at least you will get to know how it works. But that's the only way. But we are simulating, so we don't have the real building, and we're not using the blower door test. So what can we do? We have to go to ARCH360, as always. So ARCH360 62.2, they have this map and this table. Okay, so what does it mean? It means that it divides the United States, the country, into different zones, and each zone that depends on the wind speed. Okay, so we have zone 1, 2, 3, and 4. So those are different categories depending on the wind. I am not an expert on the United States geography, but I think zone 1, it's probably the worst. It's because we have this tornado alley. Okay, so especially in fall, there are a lot of hurricanes or whatever that go through the Gulf of Mexico all the way up. And I think this area is very windy, apparently. Then we are in zone number 2. So this white, it's zone number 2. So we can have high-speed winds. It doesn't mean that the wind is always blowing at high speed, but at certain moments we can have this. And apparently the safest zones are these. Okay, this is what ARCH360 says, what I believe it. So how does it work? First, we need to know what zone we are in. So if we are in New Hampshire, probably this is zone number 2. Okay, and then that depends on the building. Okay, so zone number, this number, it depends on the area, on the geography. And that depends on the building or the city. So we have exposed buildings, normal buildings, and well-shielded buildings. So exposed building, imagine that we have a building at the top of a hill. So this is a very exposed building because it's not protected at all. So the wind can blow in each direction. Well-shielded is when we are in the middle of a city, downtown, with attached buildings. Those are well-shielded buildings. And the rest of buildings are normal. Okay, so if we are analyzing a building in Main Street, I would say that it's well shielded because we have buildings around, so it's protected against the wind. If we are in the middle of nowhere without trees and on the top of a hill, I would say that exposed. And for the rest of the buildings, I would say normal. Okay, if we are analyzing one of these single family houses, I would say a normal exposure. So we are in zone 2. Then we are in normal exposure. What's this building? I don't know, space. It seems to be in the middle of nowhere, but I would say normal, okay, because it won't be on the top of a hill. It's a detached building, so we don't have buildings attached to this one. So I would say that for this one, we can use the normal exposure. And then we have the N factor table. This is number of stories. So we have 1, 1.5, 2, or 3. What if we have a high-rise building? Well, this is in a different category. Okay, so we have 1, 2, 3 floors, and that's fine. So our building has 1 floor. So if we are in zone number 2, normal exposure, and one floor, so that value, this N factor, would be 18.5. Okay. So let's write it down. 18.5. And now this is the factor that I have to introduce in my Excel file. If I open this Excel file, here there is a table for infiltration. Okay, so there are some cells with infiltration, and this is the N value. You see, 18.5. Okay, then what is this ACH 50? The ACH 50 is the value that we get from the blower door test. Okay, so if we have a building, an actual building, and we are, and if we work with this blower door test, how does it work, or what does the blower door test do? So for the blower door test, we are testing a room. Or yeah, usually we're not testing the whole house, but a room. So we apply here at the door or a window, and we have a fan, and this is the internal pressure, and this is the outdoor pressure. Okay, so when we do the blower door test, we extract air from the house so that the difference between the outdoor pressure minus indoor pressure is 50 pascals. Okay, so if we have this, when the difference between the outdoor pressure, this is the atmospheric pressure, it's the pressure that we have outdoors, and the indoor pressure, we are extracting air. So if we are extracting air, we are reducing the indoor pressure. So at the point in which we have this blower door test, we have a meter, and we say, okay, so that's 50 pascals. When we have 50 pascals, we have to look at the infiltration rate. And how can we measure that? Because when the pressure here is much lower than the pressure outdoors, through the cracks of the building, or we are having infiltration. Okay, so that's the way we have to have an actual value, an objective value of what the infiltration is. But we need to test all the buildings because the difference between the outdoor pressure and the indoor pressure is not the same in all the buildings in the world. It depends on the wind, it depends on the exposure of the building, it depends on a lot of things. So when we have an equipment that can control the difference between outdoor and indoor pressures at 50 pascals, then we can measure that infiltration rate. Okay, so we do this. We have the same procedure in all the buildings in the world, and then we can test if the building has infiltration issues or not. Okay. The thing is that we have a number here, 4. So that means that we have 4 air changes per hour at 50 pascals when the difference of temperature is 50 pascals. Okay, what does it mean? How can we, because we don't have 50 pascals in normal conditions, there is no 50 pascals is a lot of difference, okay? So we don't have this difference in real life, in real buildings. So what do we have to do? Well, the ARCH360 gives us this formula between to calculate the ACH, the air changes per hour, at normal conditions, natural. Okay, so we don't have the equipment sucking the air and expelling the air outdoors to create this pressure difference. So that's why we have this. So the formula that they propose, it's very simple. We have this value from the blower door test. We have N, which is the value that comes from N factor that comes from this table. And we only have to divide this divided by N. And here we have the air changes per hour due to infiltration. So that's what we have here. Okay, so this is the air changes per hour. This is the N value, 18.5. And this is ACH at 50 divided by N. But now we have to turn this value, air changes per hour, we have to turn this into CFM, which is cubic feet per minute. What is the what does it mean, air changes per hour? It's the volume of the house, or the volume of the room, the house, whatever we are testing, divided by 1 hour. Okay. What volume? This volume. The internal volume. So if we have in this example, we have 0.21 air changes per hour, because at 50 pascals we have 4 divided by this factor that depends on the building, the exposure to the wind, and the number of floors. So in normal conditions, we will have 0.21 air changes per hour. But now here we have to type the volume of the building. Where can we find the volume of the building? Here. Okay, so if I place the tags here, what's the volume of that building? The volume of all the spaces. So I can use the calculator. So this has 1323 plus 1254 plus 883 plus 1924. Okay, so the volume of this building, it's 5384. So I have to type here 5384. And then we turn this value into CFM, cubic feet per minute. So what does it mean? What's the volume of my building? The volume of my building is 5,384. Okay, so this is the infiltration. So this is the air that enters the building in 1 hour. So what is the CFM per minute? Okay, so we have 5,384 square feet, cubic feet in 1 hour. Now I have to find out how many square feet per minute. So that means, if I'm not wrong, 1 hour are 60 minutes. Okay, so we have to divide this by 60. So if I divide this by 60, then I have 5,384 divided by 60, and we have 19.4 CFM, which is cubic feet per minute. Okay, so that's the explanation of the infiltration rate. And now, with this CFM, we have to go to ARCH360, and then we have to calculate the sensible and latent heat. We have these formulas from the ARCH360. These formulas, the sensible heat and latent heat, and then we have to add them up. Okay, so this is, but I need CFM because these formulas come from CFM. So for the sensible heat, we have this 1.1 that depends on the specific heat of air, and those are the units. And this is indoor minus outdoor temperature, and this is indoor minus outdoor wet bulb temperature. This is dry bulb temperature, and this is wet bulb temperature. Okay, so in this Excel file, I have these formulas for the sensible heat and for the latent heat. So this is it. This is the sensible, this is the latent, and this is the total infiltration load. So in this case, with this N, with the volume of the building, my infiltration load is 2,298. What is the infiltration load in Revit? In heating, it's 1,500. What does it mean? That probably the air changes per hour at 50 is around 3 or 2.8 or 2.7. Okay, so now we have 1,500, and here we have around 1,500 too. Okay, so this is just to understand what's going on here. How does Revit calculate this number? We don't know. I wish we knew it, but we don't know what it does. But Revit has calculated that this building has exposure to the wind, that has air changes per hour value when there's a difference of 50 pascals. We don't know what Revit does. I'm sure that there's a default and there's an explanation, but it will be very difficult to find that explanation. Okay, but we try to understand, or we try to replicate or to mimic what Revit has done. So that's what we have. Okay, and this is what ARCH360 says. This we can find out because it depends on our building. It's in this area, in zone number 2 in New Hampshire. It's what do they call it? Normal. It's not very exposed. It's not well shielded, so it's normal. So, and we have 1 floor. So we have this. Okay. Then this ACH. There is no way to calculate that number unless we have a real building and we have the blower door test. So there's no way to calculate that. But according to this, Revit has considered that this building is around 2.6, 2.7. By the way, is that acceptable, 2.7? Let's find out, because there should be like passive house requirements for air tightness. And off the top of my head, I think the requirement for a passive house building, ACH at 50 pascals, I think it has to be 0.6. I think so. Okay. So this is what our good building is. If we have a value of 2.7, which is what Revit considers, Revit has considered that this is not a very good building. So it's not a passive house building, because a passive house buildings should be 0.6. So this is actually one of the improvements that we can state in our report. But we have to understand what we are doing. Okay, so Revit, according to Revit, we have this number in winter. So if we try to replicate this number in our Excel file, we have this, we have the volume of the building. And so according to this, the result of the blower door test would be 2.7. 2.7, it's a building that it's not extremely bad. I remember that last year we did this blower door test in some of the building on campus, and that value was around 8 or 10. It was ridiculously high. Okay, so 2.7, it's not bad, but it's not a passive house building. So what you can say in the report is, okay, according to Revit, I have this infiltration, and do it in winter, because in summer it's not relevant. It's relevant in winter. Okay, so how can I reduce this? It's important because look at this. It's the second highest figure in winter. Okay, so it's worth doing it. It's worth reducing that figure. So if we add more thermal insulation to the roof, it's not as relevant as reducing the infiltration rate. Okay, so according to this, with my volume and my exposure, the ACH 50 should be 2.7. This is not passive house standards. The passive house standard is 0.6. So if we had a more tight building, then the infiltration won't be 1400. It will be 300. Okay, so this is the way that we have in the second report. Okay, so with this first analysis in Revit and the second analysis in Revit, benchmark passive house. So in passive house, we can say now that the R value should be like this. We have triple glazing with low emissivity. So we can type that the air changes per hour at 50 pascals is 0.6. Okay. So we have to propose a solution to reduce the cooling loads due to the window solar gains, and to reduce the peak coolings and heating loads. Okay, so you have to try to do that. Okay, but it's complicated. First, we need to understand what Revit has done, and then once we have a number for Revit conditions, then we have to reduce this to passive house standards, and that will be the the new infiltration load.